In a Pittsburgh steel mill soaking pit bay in 1911, a 10-ton steel ingot was descending into a furnace burning at 2,200 degrees Fahrenheit when the tong inserts lost their grip. The ingot dropped straight down into the burning gas atmosphere below. The crane operator felt it go through the cable tension before he saw anything change. The rolling schedule for that heat was gone. A recovery operation measured in days had just begun. But that was not the worst outcome a soaking pit crane operator faced on a long shift. If you're new to Steel and Sweat, this channel covers the machines and the men of American industrial history, the things that built the country and what those things cost. Subscribe and leave a comment below with the next story you want us to dig into. This is the story of the soaking pit, the underground furnace that swallowed steel ingots whole, and the crane operators who worked directly above open pit mouths, burning at full temperature, every shift for 30 years. But here is what the production record of any large American steel mill in the early 20th century does not make obvious. The soaking pit was not a peripheral piece of equipment. It sat at the exact center of the steel production sequence, and nothing moved past it unless it functioned correctly. Every ingot poured in the open hearth shop above had to pass through the pits before it reached the rolling mill. The rolling mill could not run without them, and the men who operated the pit cranes were the bottleneck between the furnace floor and the finished product, working a machine that ran continuously over a furnace that never cooled, with a margin for error that shrank with every hour of the shift. The temperature requirement was precise in a way that left no room for approximation. A rolling mill foreman could not compensate for an ingot that had not soaked long enough by adjusting his roll gap or his pass sequence. The steel either rolled correctly or it did not. An ingot that had not reached uniform temperature through its entire cross-section would reveal that fact immediately, either by splitting under the rolls or by producing a finished section with internal defects that would only become visible after the steel had already been shipped. The pit was the quality control step that no downstream process could substitute for. To understand why the soaking pit existed, you have to understand what steel looks like immediately after it is poured, and what has to happen to it before it can be rolled. When liquid steel was teamed from a ladle into an ingot mold in an American open hearth shop around 1905, it solidified from the outside inward. The outer shell hardened against the mold walls within minutes. The interior of a large ingot could remain liquid for an hour or more, and even after full solidification, the temperature distribution through the cross-section was uneven in ways that were invisible from the surface. An ingot that looked solid and uniform on the outside could have a core temperature significantly different from its surface temperature, and that difference mattered enormously for what happened next. Rolling mills worked steel by passing it between pairs of large cylindrical rolls under enormous pressure. The rolls reduced the ingot's cross-section and increased its length through a sequence of passes that progressively shaped the steel into rails, beams, plate, or structural sections. But the rolling process only worked correctly if the steel being rolled was at a uniform temperature throughout its cross-section. Steel that was hotter in the core than at the surface would deform unevenly under the rolls, producing internal stresses in the finished product or splitting apart under rolling pressure and destroying the pass. Steel that had cooled unevenly from the outside produced the same failure from the opposite direction. The soaking pit solved this problem by holding the solidified ingots at rolling temperature, around 2,200 degrees Fahrenheit, for long enough that the temperature equalized through the entire cross-section. The name came from the process itself. The ingot soaked in the heat until it was uniform all the way through, surface to core, and only then could it go to the rolling mill. Could any prior industrial process have delivered the same result without a dedicated pit furnace buried in the floor? The metallurgical requirement was not negotiable. The soaking pit was not an engineering preference. It was a physical necessity built into the production sequence of every integrated American steel mill that ran an open hearth shop and a rolling mill on the same site. The pits themselves were rectangular furnaces excavated below the mill floor level, lined with refractory-lined brick capable of sustaining continuous operating temperatures of 2,200 degrees Fahrenheit or more. A large soaking pit could hold between 8 and 20 ingots standing upright, with each ingot positioned vertically in the pit cavity. The pit cover, a massive refractory-lined lid weighing several tons, closed over the top of the pit between draws to contain the heat, and was moved by the overhead crane at the beginning and end of every charging and drawing cycle. The cover itself required careful handling. A cover set down improperly could crack under thermal cycling and expose the pit edge and the floor crew to radiant heat from below. Below the cover, the pit burned continuously on producer gas fuel through burners built into the pit walls, and the atmosphere inside the cavity was a reducing gas environment at full heat around the clock. The reducing atmosphere served a metallurgical purpose. It prevented surface oxidation of the ingot steel during the soak period, which would have produced a scale layer the rolling mill rolls would then have to work through. But that atmosphere was also a fuel-rich environment at 2,200 degrees Fahrenheit that could not be entered, could not be inspected during operation, and contained no margin for anything that went wrong inside it. The ingots themselves were large. In the American open hearth shops of the early 20th century, ingot weights ranged from 5 tons for smaller specialty products to 30 tons or more for the large structural shapes and rail sections that the big Pittsburgh area rolling mills produced. A pit holding 12 ingots of 20 tons each was managing 240 tons of steel at 2,200 degrees Fahrenheit in a rectangular cavity in the floor. When it was open, there was nothing between the men and the floor and it. The scale of soaking pit operations at major integrated American steel mills was proportional to the scale of the mills themselves. Carnegie Steel's Homestead Works operated multiple open hearth furnaces simultaneously by 1900, each producing 40 tons of steel per heat. U.S. Steel's Edgar Thomson plant in Braddock, Pennsylvania, ran a pit bay size to handle the ingot output of its entire open hearth shop. The ingots from those furnaces had to move through the soaking pits before they could reach the rolling mills, and the pit capacity had to match the pour rate or the entire production sequence backed up. A pit bay running slow, whether because of a dropped ingot, a crane failure, or a pit lining needing repair, held up the rolling mill as surely as a furnace outage upstream. The pit craneman at a large Pittsburgh area steel mill was not an isolated worker. He was the connection between the casting floor and the rolling mill, and the rolling mill superintendent knew his name and his shift schedule because the rolling mill's production depended on the pit bay running without interruption. That dependency was present on the crane platform every shift, alongside the radiant heat from below. What happens when 240 tons of steel at 2,200 degrees Fahrenheit is sitting in an open pit in the floor, and a crane operator 12 feet above it is trying to extract one ingot at a time using mechanical tongs on a cable system? The physics of that situation are not forgiving. The radiant heat rising from an open pit surface is sufficient to ignite combustible material at distances measured in feet. The atmosphere above an open pit is saturated with combustion products and radiant energy that attacks every mechanical component in the tong mechanism on every draw cycle. And the tong mechanism itself is working at the end of a cable, gripping a steel ingot standing upright in a cavity it nearly fills, with a contact surface that is itself at 2,200 degrees Fahrenheit. Leave a comment below with what you think that mechanical problem actually looked like from inside the crane cab. The pit crane at a large American steel mill was an overhead traveling crane running on rails mounted at roof level, with the cab and hook mechanism suspended below the bridge. The craneman operated from an enclosed cab with a view down into the pit bay and across the pit covers. He controlled the crane bridge travel, the cross-travel trolley, and the hoist through a set of levers and controllers that had to be managed simultaneously during any draw or charge cycle. The tong mechanism hung from the hoist cable below the cab, and the craneman lowered it into the open pit, operated the tong jaws to grip the ingot, and lifted through the full depth of the pit cavity, keeping the bridge and trolley position centered to prevent contact with the pit walls on the way up. The tong insert, the hardened contact face that actually gripped the ingot, was the component that determined whether a draw cycle succeeded or ended with a dropped ingot. tong inserts wore under the combined mechanical and thermal loading of continuous pit operations. An insert that had made several hundred draw cycles had a contact geometry that was no longer identical to its original specification. The grip it provided was not the same grip the design assumed. The wear was not uniform because the thermal loading across the contact face during each draw was not uniform, and the mechanical loading at different points in the grip depended on the exact geometry of how the tongs had seated on that specific ingot at the start of that specific draw. The pit craneman did not have direct visual confirmation of tong seating from the crane cab. He had cable tension, the response of the load as he began to lift, and his accumulated knowledge of what a correctly seated grip felt like through the crane controls. That knowledge came from experience, and it was not transferable in any formal sense. A new craneman learned by running draws under supervision until the feel of the machine was built into his body. The margin between a draw that succeeded and one that did not was communicated through the controls in signals that no instrument displayed and no manual described. The Pittsburgh survey of 1907 and 1908 documented steel mill crane operations extensively. Allegheny County steel mill records from this period show pit crane operators classified as skilled workers commanding wages at the upper range of mill labor, between $2 and $3 per day, at Carnegie Steel and U.S. Steel facilities in the Pittsburgh district. The classification reflected genuine skill scarcity. There were not many men who could run a pit crane correctly, and the mills that had them kept them. The mill's investment in a pit crane operator was not limited to wages. A man who had developed the feel of the lift on a specific machine was a man who could run that machine at full draw rate with an acceptable drop rate. Replacing him meant a period of reduced throughput, while his replacement developed the same knowledge on the same machine. The mill's production schedule absorbed that cost poorly, and mill superintendents at the Pittsburgh area, steel plants understood the economic value of an experienced pit craneman in exactly those terms. When a pit craneman left, the production numbers showed it. The pit crane operators at large Pittsburgh area mills were a recognized category of skilled worker in the mill hierarchy, not interchangeable with general crane operators elsewhere in the plant. A ladle crane operator in the open hearth shop managed a different kind of load with different failure modes. A scrap charging crane operator worked in open air with no pit below him and no radiant heat rising from the floor. The pit crane operator's skill was specific to the pit bay, to the tong mechanism, to the particular characteristics of his crane and his tong inserts, and to the operating temperature and ingot specifications as mill ran. The Pittsburgh survey's field interviewers recorded accounts from pit crane operators who described their relationship to the work in terms that went beyond wages. One operator, interviewed in Allegheny County in 1907, described the job as work that required knowing the machine the way a craftsman knows his tools, and noted that a new man could not be trusted on the pit crane until he had run enough draws to develop what the operator called the feel of the lift. That phrase appears in multiple accounts from different mills. It described the same thing in each case, the accumulated physical knowledge of what a correctly seated tong grip felt like through the crane controls at the start of a draw, and what it felt like when it was not right. The feel could not be written in a manual. It had to be built by doing the job until the machine's behavior became knowledge the operator carried in his hands. But the skill premium did not change the operating conditions. The pit crane operator worked a 12-hour shift on a platform positioned directly over the pit bay. The pit covers opened and closed throughout the shift as ingots were charged and drawn, and each open cover exposed the cab platform to the radiant heat rising from the pit cavity below. On a bay with multiple pits operating simultaneously, the platform temperature during peak production reached levels that made the cab environment difficult to sustain for the duration of a shift. The steel mill workers documented in the Pittsburgh survey's 1907 field interviews described soaking pit crane work as among the most fatiguing in the mill, not because of the mechanical demand of operating the crane controls, but because of the sustained, radiant heat exposure that accompanied every draw cycle in an active pit bay. How do you maintain the precision of tong seating judgment after 6 hours of radiant heat exposure in a cab directly over open furnace pits? How sharp is the feel through the crane controls in the 11th hour of a 12-hour shift when the pit bay temperature has been elevated above 100 degrees since the first draw of the morning? Leave a comment below. If you're finding this history as important as anything we've covered on this channel, go ahead and hit subscribe right now and leave a comment below with the next story you want to see. The Pittsburgh survey interviewers who documented steel mill working conditions in 1907 and 1908 recorded the soaking pit bay as one of the most consistently difficult environments in the mill, not because of single acute danger events, but because of the sustained combination of heat, duration, and precision demand that characterized every shift from the first draw to the last. Fatigue. On the pit crane platform was a specific and documented problem in American steel mill operations of this period. The Pittsburgh Survey's industrial accident analysis for Allegheny County steel operations between 1906 and 1910 showed a consistent pattern across all crane operations in the mill. Accident rates for crane-related incidents were disproportionately weighted toward the second half of 12-hour shifts. The mechanically identical operation, same crane, same pit, same ingot specification, produced a higher rate of error in the hours after the midpoint of the shift than in the hours before it. The survey authors attributed the pattern directly to fatigue accumulation in skilled operations that required sustained precision judgment rather than physical exertion. The long turn made this worse. Steel mill workers in the Pittsburgh district worked the long turn every 2 weeks. A 24-hour shift worked when the day turn and night turn exchanged without a rest day between them. A pit crane operator in the long turn was making draw judgments in hour 20 of a 24-hour shift over open pits burning at 2,200 degrees Fahrenheit, with tong inserts that had accumulated wear across every draw since the start of the shift. But a dropped ingot in a soaking pit was not a recoverable situation in the normal sense of the term. The ingot at the bottom of the pit was at furnace temperature, in a reducing gas atmosphere, and in a cavity that was itself still burning. The pit could not be approached while operational. The recovery sequence required shutting down the pit, cutting fuel to the furnace, and beginning a cooling period. A large pit loaded with mass at 2,200 degrees Fahrenheit did not cool quickly. The refractory brick lining, the ingots themselves, and the thermal mass of the surrounding pit structure held heat for an extended period, and the pit could not be entered by workers until its internal temperature had dropped to a level that was survivable. That process was measured in days, not hours, depending on the pit size and the circumstances of the drop. When the pit had cooled enough for entry, a recovery crew went in to rig the dropped ingot for extraction. The ingot had fallen through a pit, loaded with other ingots standing upright, and depending on the circumstances, it might have displaced one or more of them, or come to rest in a position that made conventional tong rigging impossible from above. The refractory brick lining of the pit walls and floor absorbed the thermal shock of the drop and the subsequent rapid cooling, and pits that had experienced a hard drop frequently showed lining damage that required repair before the pit could return to service. A lining repair extended the recovery timeline beyond the cooling period alone, and a pit returned to service with a cracked or spalled lining would fail again sooner than a pit in proper condition. The production cost of a dropped ingot was not limited to the ingot itself. The pit that had been shut down for recovery was out of production for the duration of the cooling and recovery cycle, and in an integrated mill where the rolling schedule depended on a continuous flow of soaked ingots from the pit bay, the downstream impact ran through the entire rolling mill shift. Carnegie Steel's Homestead Works and the U.S. steel plants in the Pittsburgh district ran their rolling mills on tight production schedules that depended on pit throughput, and a pit shutdown lasting 2 or 3 days represented a production loss that could not be recovered within the same rolling campaign. But the economic pressure this created was understood at every level of mill management. Pit throughput was a production metric that mill superintendents tracked directly, and the pressure to maintain throughput translated into pressure on the pit crane operators to keep the draw rate up and minimize the time Each pit cover was open during the charge and draw cycle. A draw cycle completed quickly was also a draw cycle in which the pit crane operator had spent less time confirming tong seating before committing to the lift. The economic incentive and the mechanical safety margin pointed in opposite directions, and both were present on every shift. The demand for steady throughput shaped every decision on the floor. The ingot drops that were documented in Pittsburgh area mill records during this period show a consistent pattern in their recorded causes. Worn tong inserts, a hook catch that had not fully seated, a moment of inattention during a late shift draw. Each cause was mechanical and each was preventable, and each had been present in the operating environment for the entire shift before the draw that failed. The inserts wore on every draw. The seating geometry degraded with every contact. The operator's attention eroded with every hour of heat and duration. The drop was not random. It was the accumulation of known factors reaching a threshold at an unpredictable moment during a shift that had given no particular warning that this draw would be different from the last 100. The soaking pit technology, standard in American integrated steel mills by 1910, remained the primary method of ingot preparation for rolling for the next several decades. The pit crane operations at large U.S. Steel and Bethlehem Steel facilities continued on 12-hour shifts through the 1930s, when union agreements in the steel industry began to reduce the standard shift length. The pits themselves ran continuously until continuous casting technology, developed in the mid-20th century, eliminated the ingot production step entirely. Continuous casting produced steel in strand form that could go directly to the rolling mill without an intermediate solidification and reheating cycle, and the soaking pit became obsolete, along with the ingot molds and the stripping cranes that preceded it in the sequence. The soaking pits at Carnegie Steel and U.S. Steel facilities in Pittsburgh and along the Monongahela Valley were decommissioned as the mills converted to continuous casting through the 1960s and 1970s, and most were eventually demolished, along with the open hearth shops they had served. When the last open hearth shop in the Pittsburgh district closed, the pits that had served it went cold for the final time. Some of the pit structures remain underground at former steel mill sites across western Pennsylvania, sealed below building floors or parking lots built over what were once working mill sites, still lined with the refractory brick that ran at 2,200 degrees around the clock for 50 years. The pit crane operators who worked those pits are gone. The rolling schedules they kept moving, the ingots they drew and charged across 30 years of 12-hour shifts became the steel in American bridges, buildings, railroads, and ships. The pits that held that steel are still in the ground. The steel workers who ran the soaking pits built America one ingot at a time. If these are the stories that matter to you, subscribe to Steel and Sweat and leave a comment below with the next story you want us to dig into. Thanks for watching.